All right, everybody, we're going to begin our Q&A panel. So my name is Mia. I'm a second-year grad student here at Caltech. We have Nikita, who is a third-year grad student, Marianne, who's a postdoc, staff scientist, postdoc, and then Dylan, who is another third-year grad student. So we've written a couple of the things that we consider ourselves to be somewhat expert in, that we know maybe some things about. But feel free to ask us any questions about astronomy, about space, about the universe in general, and we will do our best to answer. So do we have any questions?
How big is the universe?
How big is the universe? Great question. I feel like I've been talking a lot, so I'm going to hand it off.
So we don't really know how big the universe is because we can't see all of it, but the observable universe, so the bit of it that we can see, is about 15 billion light years because it's about 15 billion years old, so the light has traveled about 15 billion light years, give or take a bit because it's expanding, so that makes everything kind of funky, but more or less 15 billion light years, which is a lot, and I have no clue what that is in meters or miles.
It's a lot, basically.
I know I question that theory all the time. I did with my brother Joe. He was really good at it too. Like, how big is it? Is it expanding? I don't think so. I think it always was. See what I mean? I think if you go far enough and fast enough, you'll be looking at yourself. Somehow. You know, I kind of see that. But there again, everything's theory. You know, that's what we think. A light year is 186,000 miles an hour. Radio waves faster, right? It is. It's faster.
So radio waves move exactly at the speed of light.
It's faster than the speed.
No, exactly at the speed of light.
It's before. It's one moment after, when the nuclear bomb goes off, the radio wave is so fast, it hits you, and the light goes off and fries all your electronics. Radio waves fast.
Yeah, yeah. So we had another question here.
I don't know.
Agree to disagree. Yeah. So you used the figure of 15 billion light years. So, you know, I generally understood the age of the universe to be about 13.8 billion years. I vaguely remember recently seeing something about that some new discovery that may alter that timeline. I'm just wondering if your 15 billion year estimate is counting for that, or are you just using a rounder number?
I was just rounding it off.
Yeah, so I guess like a big thing in astronomy is that unless you work in very specific fields, and the expansion of the universe is actually one of those fields. Like you can get some numbers in astronomy to, you know, very precise values, right? You can get like 2 or 3 decimal places and be confident in that third number. But in many cases, you really only have like 1 decimal place worth of like significance in your measurements. And so 15, 13, close enough. Yeah. Except in this case it is, yeah. In this case it is 13.8 billion. Yeah, it's like 13.8 plus or minus 0.0 something. Yeah. Yes. Mm-hmm. Great question. Okay. So radio astronomy is essentially looking at the part of the electromagnetic spectrum that is radio waves. So radio waves are just a kind of light, right? And what I do specifically is I use radio telescopes are basically these giant satellite dishes, sort of like Dish Network, right? And you know, all of your like satellite TV is broadcasted on radio waves, for example. All of your GPS is broadcasted on radio waves. What I do is I take these dishes and I point them, not myself, but I tell our wonderful telescope operators to point them at like nearby galaxies, for example, to study, you know, what sorts of astrophysical phenomena produce these radio waves. So some of the things that I've looked at are when you have stars that recently formed. These stars are going to give off a lot of light that knocks electrons off of hydrogen. And essentially what you get is this soup of like electrons and protons floating around. And when they, whiz and fly by each other, you get this radio emission that comes out. And that's one of the things that I look for. Actually, if you see how strong that radio emission is, you can actually measure how fast the stars are forming. So that's one thing that I do. Another thing that I do is I look for the relics of supernovae, for example. So when a star explodes, it's going to eject a lot of its mass, right? And that mass is going to impact the gas that's around it. When you have two, the gas is moving kind of slowly, and the ejector moving really fast. So think of it like a traffic jam where you're just driving 80 on the highway, and then all of a sudden you have to slam on the brakes. Except you can't slam on the brakes when you're just gas, right? So you actually crunch right into that slow gas, and that collision produces lots of radio waves as well. And so those are the two things that I look for. And radio astronomy is much broader than that, but that's sort of my experience with it.
So, you asked about active galactic nuclei. So, in the most broad sense, what I study are black holes. And black holes come in a range of masses. There are those that are formed from the deaths of massive stars. Those are stellar mass black holes, which you find in our own galaxy and other galaxies. But the kind of black holes I study are supermassive black holes that are billions of solar masses. And we believe that every galaxy in its center harbors a supermassive black hole. But I studied those galaxies that are so bright, and the reason why they're so bright is because they have a supermassive black hole at their center that's being powered by accretion, basically the infall of matter in the form of a disk onto that black hole. And as a result, a lot of radiation is emitted, and that's why they're so luminous. And these types of galaxies are called active galactic nuclei. And I specifically focus on studying them in the X-rays, and this is because active galactic nuclei, while they're quite bright at the wavelengths that we can see in the optical, they're also super bright in the X-rays. And I use this really cool telescope in space called NuSTAR, which is an X-ray telescope that is the only telescope capable of focusing high-energy X-rays. And it's really cool because with X-ray astronomy, you can probe a lot of properties of these supermassive black holes, like what's the geometry of the black hole and the material surrounding it, how is the matter falling onto it, all sorts of cool things, studying temperatures and all sorts of other properties. So yeah, I look at the more observational aspect of black holes.
Could we get are there any people who haven't asked any questions before who might want to ask? So maybe in the back. Sorry, you already asked the questions.
So when a supernova occurs, you said it excites the gas. So besides the radio waves, does it cause any sort of other reaction in the area?
Yeah, so the question was, when a supernova explodes, do you get, what are the sorts of radiation that you get out? Is that a fair...
aside from that, what else occurs? Anything else? Does it simulate other reactions?
Yeah. So what kinds of reactions do you get when a star explodes, basically? So in the early days, what happens, so you have this star, and this is going to be a core collapse supernova. This is a specific kind of supernova that I'm talking about. A star is basically like an onion, right? On the outside, you have layers of hydrogen, and then you have layers of helium, and then you have layers of carbon, and then all the way to the center, where you have layers at the center of iron. Yeah. So what happens when you build up that iron core is eventually it gets too massive, and it can't support itself, because it turns out that nuclear fusion, you can fuse iron, but it actually takes energy instead of gives energy. And so the core starts to collapse, and that collapse happens starting from the inside out, right? You start having the core collapse, and then all of a sudden there's nothing holding up the rest of the star, and the rest of the star starts falling into this core as well. And you just get crunching and crunching and crunching. And eventually, some of the stuff, and what stops the crunching is that either the center turns into a neutron star or a black hole, and we can get into that later. But essentially, you start, if it's a neutron star, you start getting things that bounce off the surface. And that sends a shock wave going outwards. And so that's the first thing that happens in a supernova. It's the first reaction, if you will. And so that shock is basically going to start ramming into the gas that's still falling in. Okay? And eventually it's going to reach the surface. And at this point, you get this intense flash of X-rays. And this is called shock breakout. And this only lasts for about like 10 seconds or like a minute or something like that. And there's only, I think, ever been like one or two that's ever been observed of these shock breakouts. But we think that they happen in every single supernova. And by the way, with these new wide field surveys, we're taking images of the sky like, you know, every night, basically. Every 3 nights, actually. There's a telescope that will, on Palomar Mountain near San Diego, that will give you an image of any part of the sky that you want. That's observable from Palomar Mountain. Anyways.
That's an aerodynamic shock wave? Like a hydrodynamic shock wave?
It's a hydrodynamic shock wave, that's right.
What generates the X-ray?
It's basically this large change in density, right? You accelerate the particles to high energies. And this is the shock breaking out of the...
When it stops, it slows down and has to give off an X-ray?
Yeah, essentially. Yeah, you're superheating the very thin layer at the top of the star. So anyways, we're finding like, you know, several supernovae per night, right? And this is so fast that we've only seen like 2 of them ever. So that's the first thing. 2 shock breakouts. But we think that they happen in every supernova.
Actually, did you record them? Did you see them where?
Yeah. So one of them, there was a student at the time who's now a professor at Harvard. I'm blanking on her name. What? That's right, yeah, Alicia Soderberg, who just happened to be pointing an X-ray telescope at exactly the right moment in a galaxy where a supernova just happened to go off exactly at that time. It was like 1 in a million, like incredible luck, right? And there's another one where I think an amateur astronomer just happened to be taking a picture, like with their telescope of this nearby galaxy, and they just happened to catch that as well, just in their picture. Anyways, I think those are the 2 examples. There may be one or 2 more, but I can't think of any. So that's the first thing that happens, is the shock breakout. And the next thing that happens is you start getting lots of gas that's just this big, like, you know, ejecta that gets sent out from the explosion. And that is going to be expanding and giving off lots of light. And at first the light is just from the heat of the gas, but oftentimes what you get is this radioactive decay, because you have lots of nickel-56 that is produced in these explosions, and those will decay eventually to iron-56. And that's sort of what powers a lot of these supernovae in visible light for a long time. And then afterwards, once the visible light decays away, then you may or may not see this radio signal that I was mentioning before that I look for. And you only see the radio signal, essentially, if you have enough gas, like, you know, clumps of gas or something, that just happen to be outside of the star, enough for this ejecta to slam into. And if there isn't enough gas, then it'll be too faint in the radio for us to detect.
Well, how hot? How hot? How many Fahrenheits? How hot? How hot is it?
How hot is a supernova? Yes.
Yes. So the initial, like the shock breakout that Dylan was talking about, is, if I get this, is very hot. It's like about 100,000 Kelvin, which is probably like 200,000 Fahrenheit, or at least, actually at that point, I don't know the conversion anymore. It's just times 2, right? Times 2. So like 200,000 Fahrenheit. But it cools down very quickly. So the actual, yes. So the actual, what happens after when it actually starts expanding, it's more like 10 to 20,000 Kelvin, so that's 20 to 40,000 Fahrenheit, something like that.
That is amazing. It really is.
Thank you all for this panel. You're very brave to expose your knowledge to us. We appreciate it. I just want to say that. And I'd like to ask, I saw black holes on both Nikita and Marianne in your research. I was wondering how much the theory of relativity applies to your field. Is it general theory of relativity? As a layman, I was just thinking about it when I saw it.
So I think it might. Oh, right. Sorry. So the question is, how much does general relativity apply to the research of black holes? So I think both Nikita and I do mostly observational research, and I guess it actually applies more to yours than to mine, because I look at optical and infrared light, which is coming from farther away, and the general relativity is mostly important, like very close to the black hole, and does matter in the X-rays. So.
Yeah, so GR effects are pretty important. So just, like the nature of the space-time around the black hole, we know that most black holes are rotating, so they have some kind of spin. So, there are, certain geometries that we apply called a Kerr space-time to describe that. Like Marianne was talking about, once you start to get close, really close into the black hole, so you have the black hole, and then there's the event horizon where once you pass that, light cannot escape, and then you have innermost stable circular orbit where you can have stable orbits of particles around the black hole. So, at those very inner regions, GR effects really begin to manifest. So one thing that you see is light that's emitted from very close to the black hole becomes gravitationally redshifted. And what that means is that basically, if you imagine a wave packet of light, it's basically the wavelength is being stretched out because of the space-time around that black hole and taking into account general relativity. The fact that matter close to the black hole is rotating very rapidly produces a lot of features again. For example, when we look at these things in the X-rays, there's a lot of iron that's usually near the black hole. And so this iron can fluoresce and emit radiation. And if that iron is coming from very close to the black hole, then the shape of that line profile can get stretched out a lot because of these gravitational redshift processes and other GR effects. And it can be pretty tough trying to model general relativity when we're looking at these things either in the X-rays or just generally trying to do simulations of like photons of light and how it interacts with the accretion disk and further out. But yeah.
So one last thing about the GR is that, of course, you may have seen the picture of the black hole recently, right? So that was in more like almost radio light, but that was light that was coming from very, 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 very close to the black hole. And without GR, it would look completely different. So that's very important there.
You've seen an actual picture, Steve?
Yeah, so there's this big thing in the news, this telescope called the Event Horizon Telescope, which is not one telescope, but many telescopes all over the Earth. They're like a set of radio dishes that basically was staring at both the black hole at the center of our own galaxy, and what the huge press release in the news was all about was it also imaged basically the black hole event horizon in a nearby galaxy using this array of radio interferometers. And yeah, so without general relativity, you can't basically, it was basically another test of general relativity, the fact that we could image this black hole. And another interesting thing is like the resolution of that image is the same as if you were trying to read off the date on a coin in New York from LA. So that's the level of resolution we're achieving with that image.
Yeah, it was about, probably for you, star formation. It was mentioned in the lecture when the gas breaks down, it was said that a certain amount of radiation is required to start the production of a star. And that radiation gives off heat, which makes the rest of the formation, or rest of the stars begin. What temperature is required to go from gas to the radiation which produces the star?
So the question is, at what temperature can you go from a clump of gas to a star? So in order for a cloud, like the big ones that he was showing, to begin to collapse, you actually have to have a very cold cloud. So we're talking 10 Kelvin, which is minus 260 degrees. What about Fahrenheit? What's that in Fahrenheit? It's below freezing. It's very, very below freezing. And then when you're at, so that's when, in order to get the cloud to first collapse, you have to be at minus hundreds of degrees Fahrenheit. And then in order to get the star to form, so as he mentioned, you do have to have some radiation. It has to heat up so you can get fusion. And the reason for this is because you need particles to be moving very fast so that they can fuse. Otherwise, if you have two hydrogen atoms, they're both positive charges, and positive charges don't want to be near each other. So they need to be moving very fast. And for that to happen, the temperature for fusion to happen is 10 to the 7 Kelvin for hydrogen, which is 100 million degrees Kelvin, which is basically 100 million degrees, 200 million degrees Fahrenheit. 10 million. Wait, what did I say? I said 100. Oh, I'm sorry. Yes, sorry. 10 million. Okay. It's massive. It's hot. Yeah. Did that answer your question?
Yeah, but and also oppositely, how cold can it possibly get before clouds even? Is there a max free cold temperature in space?
So what's the coldest temperature you can get to in space? Yeah, good question. So the coldest you can really be ever is absolute zero. So absolute zero is 0 degrees Kelvin, which is minus 373 degrees Celsius, which is minus 600 or so degrees Fahrenheit. Okay, we're going to check what it is in Fahrenheit, because we don't do that.
So the cold temperature barely is in effect to how hot they get.
Sorry, what?
As far as the range of temperature and as far as our existence, we're very cold.
Yeah, I would say we're 460 Fahrenheit. Okay, yeah. So the range of temperatures in the universe can basically go from very close to absolute zero. So in these clouds, you're at a few degrees above absolute zero, to, as I mentioned, 10 to the 100 million. Yeah, no, 10 million. Oh my God, 10 million degrees. So I guess you could say that we're on the cold end, but I think it's more interesting to think about how it's a very specific range, right? A few more degrees hotter and we would die. Yeah. And so this is almost certainly due to the fact that life as we know it can really only exist in this range of temperatures. So one thing that we do when we look for life on other planets, for instance, is we look for planets that are in the right temperature range. So in the right range for liquid water to exist, for instance. Yeah. So we had a question up here.
Just going back to the black holes, two questions actually. The first was with regard to that image. My understanding from the image is that what you're seeing there, the black hole, in terms of size, it extends somewhere out to like the orbit of Saturn or thereabouts, overlaid on the solar system. So the first question is, given that black holes are just by definition incredibly dense and like have tremendous gravity, what is our understanding of the range in size in terms of like the radius of black holes? Do you have an understanding of that relative to the radius of the sun? The second question is just, you alluded earlier to the fact that you think that, this is my theory, scientists think that supermassive black holes are at the center of they are necessary for the formation of galaxies, or is it that they have formed within galaxies and then they somehow end up in the center because of their gravitational so either.
Right, so about the ranges of how big a black hole is, this is actually one of the few things. So assuming that general relativity is correct, which so far it clearly seems to be, we actually know the sizes of black holes pretty well. At least we know the size of what we call like the event horizon, like what we call the Schwarzschild radius, actually, which is basically where the place where light can no longer escape. So where and that's just a simple, it scales with the mass of the black hole. So if you would have one solar mass of black hole, it would be, I always forget this, like 2 miles, 3 kilometers? Radius or diameter? Well, right, so a mile in diameter, it's 2 miles across. So that's one solar mass. The Earth would be like 3 centimeters or something. And then if you scale up, it just goes linearly. So black holes that you form in a supernova explosion that are like maybe 10 times the mass of the sun, they'll be like 30 miles across. Black holes like the one that we took the picture of, well, not us, but people, it's like 10 billion solar masses or something? Well, order of 1 billion solar masses, so that would be 1 billion times bigger than 3 miles. So that's why it's like the size of the solar system, basically. It just scales linearly with mass. So, and the mass ranges from like 5 times the mass of the sun to 10 billion. So that's also the kind of range. It's an enormous range, yeah. Yes. Yeah, exactly. Kilometers to the size of the solar system, basically.
And then the other question about the center, the supermassive black holes at the center of the galaxy.
Yeah, so like we said, we think that supermassive black holes do reside at the centers of galaxies, like Mike mentioned in his talk. The way we think galaxies form is, we have, a large amount of material that infalls within these gravitational wells produced by dark matter, and then that infalling matter shock heats and then cools, and then you end up with a rotationally stable disk. So, the questions about how supermassive black holes form and reside in galaxies is another big open question in astronomy. We see supermassive black holes with masses of billions of solar masses forming very, very early on in the universe. And a huge question is, we don't know how these black holes gained so much mass in such a short amount of time. There are a lot of popular theories out there. One is that you just have, matter just directly infalling due to gravity, and just keeps on collapsing in on itself, and then you just end up with accretion of material to further feed the black hole. Other possibilities is that there are a population of very, very massive stars. In that plot that Mike showed in his talk of like the number of stars that you see as a function of mass, so ones that are at the very, very upper end of that, and those stellar remnants could be the seeds to form these supermassive black holes. But it's still a big open question of how you can, basically feed matter to produce such massive black holes so quickly, so early on in the universe. That's a big question. Again, there are supermassive black holes that, are believed to reside in every galaxy, but the level of accretion or the amount of matter that falls into those varies from galaxy to galaxy. I study active galactic nuclei, which are so luminous because they have, these large accretion disks. They have large-scale accretion happening, and a few solar masses of material falling on these things per year. But then you have our own Milky Way, which isn't an active galaxy, and so we don't even know if there's an accretion disk around it because it's not as luminous as these other kind of active galaxies that I study, and so it's unknown how matter is being fueled, and how galaxies can transition from quiet phases to more active phases.
So I also just wanted to add to that, not every galaxy has a supermassive black hole at its center. So the galaxies that I study, dwarf galaxies, these are galaxies. So the Milky Way has about 100 billion. 100 billion stars or so. Other galaxies, the ones that I study, have many fewer stars. So anywhere from 10,000 stars to 10 million stars, which is much, much less than 100 billion. And these dwarf galaxies, we don't think they have supermassive black holes. We've never seen any sign of it.
Could that be a reason why they're dwarf galaxies, that they don't have this gravitational power source, essentially, for them to attract more?
Yeah, so the question of how galaxies form, I think, is really, really open. Yeah, Miriam.
Yes, so there's not so much, I mean, there are clear relations between the mass, for example, of the supermassive black holes in galaxies and the masses of the galaxies themselves. But we don't think that you need, the black hole doesn't form the galaxy. The galaxy forms because you have this huge dark matter cloud that basically attracts gas. And so it's very much an open question, like how do so the galaxy shouldn't care about the black hole. I mean, the black holes are very massive, but they're still only a tiny fraction of the total mass in that galaxy. And most of the stars, for example, in the Milky Way, our sun doesn't care at all about that black hole in the center. Only like the nearest, maybe a couple thousand of stars actually care about that black hole. And everything that's a little further away just sees a whole bunch of mass, and most of that mass is actually in the stars. So you don't need a black hole to form a galaxy, but they somehow influence each other. So we think that one of the ways maybe is what Nikita is studying is these active galactic nuclei. They actually can launch pretty powerful winds, and they might help in driving gas out of galaxies, but it's not entirely clear how that works, if that happens. So it's funny. We don't need black holes to form a galaxy, but they definitely form and evolve together, and we just don't understand how it happens.
Yeah, just to give a little bit of sense of scale, the radius of influence of the central black hole in our galaxy is something like a light year or like a couple light years compared to like our sun, which is like 24,000 light years away from the center of the galaxy.
Well, the sun is orbiting the center of the galaxy.
It is, yeah, but it's mostly orbiting like the distribution of mass, like that it's the stars and dark matter inside. It like does not care at all that we have a 2 million solar mass black hole in the center of our galaxy. Yeah, we had a question in the back. What happens when a black hole dies? Great question.
So black holes are basically a dead star, right? It's already dead. It usually doesn't really die again, so the mass just sits there, and it probably stays there. So there is this idea that Stephen Hawking had about Hawking radiation. So black holes can radiate a tiny little bit of radiation, and very, very, very slowly, if that goes on for long enough, that will eventually like evaporate the black hole. So it will lose mass to this radiation. But in practice, the black holes that we have, like the ones that are, even the ones that are pretty small, that are a few times the mass of our sun, they will take many, many, many times the age of the universe to actually ever evaporate. And in fact, many of them are feeding at the moment, so they're growing rather than shrinking. So the one place where this is pure speculation, well, no, sorry, it's theory. I'm not allowed to call it pure speculation. But so the idea is that maybe in the beginning, in the Big Bang, or right after the Big Bang, they formed these, what we call, what do you call them? Primordial black holes, thank you, Dylan, that are like Himalaya mountain-sized. So they're pretty small for a black hole. They're like a couple, whatever, several thousand kilograms, but, you know, much smaller than the Earth. And if those exist, and they didn't really do anything since then, they would be evaporating right about now. And then some people think that that may go with like a flash of gamma rays or whatever, but we've never seen anything that looks like it, and we have no clue if these black holes ever existed in the first place. So we don't know if they were formed. We don't know if they exist now. We haven't seen anything that looks like them, but well, we know that very massive black holes exist. we don't know if these tiny Himalaya-sized black holes exist.
Yeah, black hole to me is a negative. Okay? You take a positive or a positive and a negative, X-ray or not, in my opinion. See what I'm saying? I want to shoot towards that black hole because I want to go to that galaxy. Slingshot.
That would be a very interesting experiment.
Oh, it didn't work. You're gone. That's
Yeah.
the way I think. Like,
Yeah, if you aim carefully enough, you might end up inside the black hole.
energy sucking. Hey, we got something sucking our energy. Let's check it out. Let's slingshot over that.
You were talking about iron being near the black hole. Is there a elemental distribution closer to the black hole for some reason? Because you're talking about iron being near.
Yeah, it doesn't necessarily So the question was, when I was talking about iron being near the black hole, is there some sort of distribution of iron? Is it more concentrated?
Different elements. And
Okay.
Distribution of elements that, for some reason, I just don't know why. It seems gravitationally it wouldn't be different.
Yeah, there are definitely other elements besides iron present near a black hole. Hydrogen is the most abundant element in the universe, and it is pretty ubiquitous near the black hole, but it would be because it's such a high temperature near there, it would be in an ionized form, so basically just protons and electrons. You do have other chemical species like oxygen, neon, all these other elements. If you take a spectrum, in the optical, you will see lines from these different chemical species. Like
There's no sort of radial distribution of elements. There's no reason why one element attracts quicker than another.
no, you don't really have like a sort of a. I mean, you can find iron close to the black hole or any other element, and you can also find it further away. And then moving away from elements, there is obviously a lot of dust within the galaxy, and by dust, what I mean is, these kind of sort of grains of particles formed from coagulation of heavy elements, essentially. And that dust there is a certain radius within which it can't exist. It would just sublimate because the temperature is too high. And so beyond that dust sublimation radius, you do see a lot of dust near the black hole, not as near as the kind of area that general relativistic effects would be happening. But yeah.
We can get a question here.
Yeah. So talking about black holes at the time of the Big Bang. So just even a fraction of a second after the Big Bang, the mass and the density was enough to create a black hole. So why didn't the universe itself just remain as a black hole at that time?
So the question is, why did the universe not remain a black hole when it was incredibly massive and dense near the Big Bang? That's about right?
So there's actually this really fun number that I forget where I read it. But if you look at the total mass and sort of what we think is the size of the universe, and you look at sort of the density, then if it were a black hole, the whole thing, then that would sort of make sense. So maybe we are all inside a ginormous black hole. Who knows? Other than that, I'm not sure if I think densities weren't high enough to really form black holes for very long. So I would assume it has something to do with things being chaotic, and also inflation happened really quickly after the Big Bang, and so everything just expanded really rapidly, and I don't think there was even time for anything to collapse quick enough.
You need the inflation to be higher than the speed of light, because we are saying that nothing can escape a black hole. Even light cannot escape.
Right, but the expansion actually happened. Well, I mean, so the Big Bang, or the inflation, which is the period of inflation, which is when the universe expanded really, 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 really rapidly right after the Big Bang, actually went. I mean, okay, it didn't really go faster than the speed of light, because that doesn't make sense, in a sense. But you were basically forming a lot of new space really rapidly. So if you were looking from the point of view of one particle, then other particles are actually moving away much faster than the speed of light. I think that. And other than that, I'm just rambling.
Kind of, yeah. Yeah.
Excuse me just for a minute, please. golf course right in front of me. I'm watching the Hellbach comet. I'm sitting there going, that thing has a bow wave on it. It's in outer space. It's a vacuum. You got to see what I'm coming at. I'm going,
Yeah, so the comet's tail comes from evaporating stuff that's coming off of the comet because there's like ices that are being sublimated off by the radiation from the sun. Anyways, to get back to your question, thanks for coming. So to get back to your question, I think, so there are a few things that are going on. First of all, you cannot move within space faster than the speed of light, or really at the speed of light if you have any mass. However, space itself can expand, quote unquote, faster than the speed of light. And that actually is like pretty normal. So in astronomy, we have this concept called redshift, which is essentially the farther away something is, the more light that comes from it is going to become reddened, simply because it's traveling through expanding space. And the space is sort of, you can think of it as stretching out the wave, right? And so above a redshift of 1, or maybe it's 2, I can't remember which like there's tons of space that's out there above redshift 1 or 2. Basically, everything else is like expanding faster than the speed of light. The space is expanding faster than the speed of light. So that's like, pretty normal. So there's this theory that Marianne mentioned that conveniently explains a lot of things about the universe. It has not been observationally tested, which is inflation, right? And it's thought that the universe, in its primordial, extremely dense state, expanded at some absolutely ridiculous rate. Like, it's exponential expansion where it, like, within the span of like 10 to the minus 50 seconds or something like that. So 0.00, like 50 zeros and then a 1 seconds. It expanded by a factor of like 10 to the 50, something like that. And so, those are not exact numbers at all. I don't think anybody really has good numbers on this, but you needed this absolutely ridiculous expansion. That's, by the end of it, the universe is no longer dense enough to form a black hole. And the other piece of that puzzle is that black holes don't form instantaneously. There's some, time that it takes for the stuff to crunch back down, right? And so in the very early universe, and you can sort of think of it as like, is the force of gravity or the energy density of gravity stronger than the other energy densities in the universe? And in the very, very early universe, it was definitely not gravity dominated. It was definitely not matter dominated. It was dominated by, other things like, whatever this inflation field is. And then it was like, radiation, I think, in the beginning? Yeah. And then it was matter dominated, and now we're dominated by this dark energy that nobody understands. Yeah.
You said earlier that when you get to the point where you're fusing into iron, fusion stops at that point because the fusion into iron takes energy rather than giving energy.
That's right.
Can you explain what you mean by takes energy? And does the iron atom retain the energy in order to hold the iron together?
Yeah, so great question. So the idea, so the question was, what did I mean back then when I said that fusing iron takes energy instead of giving energy? So usually what happens, say you fuse 2 hydrogen atoms together, is when those 2 atoms snap together by the strong nuclear force, there's a lot of energy that's released. And this has to do with like atomic physics. The binding energy of the atom, of the helium atom, is a little bit smaller than the sum of the binding energies of the hydrogen atoms. Correct me if I'm wrong. Yeah. So that's right. It loses a little bit of mass. So the mass of one helium atom or one helium nucleus is very, very tiny, like very, very, a very, very slight amount smaller than the mass of 2 hydrogen atoms. And that mass gets converted into energy. However, when you start trying to fuse something with iron, you actually start losing energy. You actually need to put in energy in order to get something to fuse with iron. And so that's what I mean by taking energy. Instead of having this release of energy in fusion, you start having this reaction that sucks in energy. Yeah.
Magnetic fields?
Yes, magnetic fields, okay.
Yeah, excuse me, sir. Excuse me, magnetic fields. Okay. Now you look at Earth, and we have ears. Go like this, magnetic field comes around like this. Okay, that's Earth. That's us. We're blue. Okay. So I look at that and I go, that's interesting. Magnetic field like that is quirky. It is. You look at that picture and you go, oh my God, magnetic field. Even with the iron plate and Earth, it's perfect. We're blue. There's a scientist over in Japan that did a radio color spectrum telescope show. It took them years, Japan. Well, scientific community like us, you, whoever, said no problem. So he finds this clear desert, chilly, 5,000 feet puppy, and he's looking for, we're blue, protein. Those are spectrums, prism. That's a prism. Those are colors. So he's looking for protein color. This is his idea. And he got all the money, he's down in Chile, Japan. Right? I think the color is yellow gold or yellow. We're blue, we're water. See what I'm saying? It's amazing, the scientific community, what they're doing. He's looking for color. You're looking for something you can't see. It's beautiful. I love it. I get excited about seeing and hearing or the latest and the greatest.
Science is pretty cool, yeah.
Yeah, it really is.
So are there any other questions?
Yeah, it is.
Yeah, we have one in the back.
You said you study small galaxies.
Yes.
What distance are they?
Good question. So the galaxies that I like to study, are the dwarf galaxies that I study, are right next to pretty close to the Milky Way. So we're talking within, oh my God. No, 30,000 light years. Thanks. That's what I have these people for. Yeah.
30,000 light years, so they're actually right there with the Milky Way.
Yes.
They're like the globular clusters.
Yes, they're actually pretty similar to globular clusters. What we think is happening, and one way that we think that galaxies like the Milky Way build up, are by glomming. So Mike showed this in one of his videos earlier. All of these small galaxies are sort of glomming onto each other and then building up into larger and larger structures. So that's one thing that makes these dwarf galaxies really interesting, is because if we can understand how they form and how they interact with each other and with the Milky Way, we can get a better sense for how the Milky Way itself evolved over time. We have a question here?
Yeah, this question is, how are galactic rotation curves measured? And how far, or how many galaxies can you see that for? So how far out can you actually measure that in the galaxy?
So the question was, how are galactic rotation curves measured, and how many of them can we measure? So I'm going to draw a galactic rotation curve on the board, if that's okay with everybody. So a galactic rotation curve is a plot that looks like this. On the x-axis, you have distance from center of galaxy. So for any given galaxy, your center is here, and you're moving out. And then here, you're looking at some speed, some velocity. And the rotation curve of a galaxy looks something like this. It's flat out for a pretty long while, and then when you get pretty close, it starts decreasing. It looks like that. So this is one way that we know that dark matter exists, is because if dark matter did not exist and all the mass was just in stars and luminous matter that we can see, if you account for all of that mass, the rotation curve of a galaxy, which is set by gravity, so if you account for all the gravity of just the stars and just the luminous stuff, it should drop off. But it doesn't. What we see is that it actually stays flat for a much longer period of time. And this was one of the very first clues that dark matter is a thing in galaxies, and it's still one of the strongest pieces of evidence for dark matter. So we can measure rotation curves. So the first question is, how are these measured? One way that we do this is by taking spectra of galaxies. So if you look at a galaxy, that's in a galaxy. If you look at like a disky galaxy, sort of from the edge, from the side, what you can do is measure at every single point along this direction. You can measure the redshift, and that tells you how far away or how fast things are moving towards or away from you. So all the stuff here will be moving outwards, out from the board, in our direction, and all the things over here will be moving into the board in that direction if the galaxy is spinning this way. And so by measuring the redshift, you can actually get this rotation curve.
Actually, it should be incredibly small redshift, right? So.
Yeah, so what we do is we look at single lines. So one common thing is, one emission line that people usually use for this is the 21 centimeter line produced by neutral hydrogen. And if you're looking at just one line and you know very precisely what that line's wavelength should be, then you can measure these very small shifts. And we've done this for, oh my god, I don't even know off the top of my head. Most galaxies that are local to us, you can observe. The issue is not distance or anything, it's really observing time. In order to get this, very precise measurement, you actually need a pretty good sub-millimeter radio telescope. Sorry. Yeah, and so these are for spiral galaxies also, right? I've drawn a pretty obvious disk here. For galaxies that are more spheroidal, this gets a little more complicated. For the dwarf galaxies that I study, I actually measure the redshifts of individual stars. And that's how I get their velocities.
How do you measure?
How do we measure this? Yes.
How do you measure?
Good question. So if we look at the light from anything, from a star, from a galaxy, it usually comes to us in the form of, let's consider just the range that humans can see, just like white light. If you break that white light into all of the colors, right, you get a rainbow.
Right.
And in kindergarten we learn, there are 7 colors in the rainbow or something. But there are many more than that, right? Color is a spectrum. And so we can actually break it down into many, many more colors than just Roy G. Biv. We can break it down into hundreds and thousands of colors to the point that we can't give them names anymore, right? Like you run out of colors in your Crayola box, and so you have to start giving them numbers. And so we give them numbers like 6563, which happens to be a pretty special color in astronomy. You give them numbers like 5007. And these numbers correspond to the wavelength of light. And by looking at the wavelength of light, we can tell all kinds of things. We can measure, so what I was talking about here by measuring these things, we're looking at one specific line in the spectrum of a galaxy. So if we say these are all different colors, all of these points, and at every point we're plotting how much light is at that color. And this particular color corresponds to this transition that happens in hydrogen. And so so we know exactly where that should happen, what color that should be, because we can study that in the labs here on Earth. And so this is how we understand that, if this line shifts a little bit, that gives us information about how fast things are moving. Does that make sense? All right.
Your curve there,
yes.
There's a linear region there.
This bit.
Solid body rotation.
Yes.
Out the sun. Why is it like that?
It's because in the center of galaxies, they're pretty baryon dominated in most galaxies. So they're dominated by not dark matter.
Okay.
And so this is pretty much as expected. Does that make sense? So, okay, here, let me redo this. So here, something like that. So it's 0 at the center because there's no mass, so you don't get any rotation. And as you go farther out, it's actually someone want to help?
It's basically like, if you do the math, you're essentially like, you treat like the inner bulge as like an onion with a lot of layers, and so as you like move out in radius, you're basically like,
Are they so gravitationally connected?
essentially the reason why the velocity increases with distance is because you have more mass enclosed within that distance when you're looking at the very central bulge, which is dominated by starlight. And then once you get out of that bulge, you still have the dark matter present, and so you don't see a fall off. You still see the velocity not continuing to increase because they're no longer dominated by all those stars in the central bulge, but you still have the dark matter that's still providing mass, and so you just see it level off.
In the central bulge, the gravitational connection is so strong, so that's how they stay together in some sense, and that's why you get the solid body rotation sort of thing. Like if you have a real solid body, you rotate it.
The whole galaxy is still, like, all the stars in the galaxy are still rotating around the center.
But I'm just saying, why is it this linear?
Because as you move out in radius, there's more mass within that radius.
But why is that? But why is it a linear function as opposed to?
Because math. I'm sorry.
There has to be something keeping it together, I think.
Which is gravity, yeah.
But as you get further out, it's less dense.
Yeah, so it's not really like it's a solid body rotation. It just happens to be that the amount of mass that you're increasing, the amount of mass enclosed that you're getting, the extra amount, happens to increase at exactly the right rate to produce roughly a flat thing. And it's not actually flat. I mean, if you look at real rotation curves, it's sort of like wiggly and wavy, like in this region. Like it's going to look, a little bit like this, right? And it's not just measurement errors. It's
Right.
Yeah.
I was talking about the linear part at the very beginning.
Oh, the linear part at the very beginning. But that also has to do with just how much mass you're taking in as you expand your volume. Yeah.
How long are you all a team?
Are we all a team? Well, all scientists are really a team in the pursuit of knowledge. Yeah. But we work in different areas. We work in different research groups.
All the way you got to make life. It's really interesting. I'm old school. I think that's all. I have reliability through experience and observation. That's all.
Well, that's what we like to do too. Yeah.
My teachers, I come from a Carmelite nun taught me the speed of light, frequencies, colors, putting a prism on her desk, taking a light, having respect, taking a chalkboard. This is before all the okay? So I'm there in 8th grade, I'm going, she says, this is the speed of light. I mean, she was really interested, right? So she takes the eraser and she turns on a projector light and darks the room. And then she says,
Is there a question
I'm
here?
going to show you that these particles will block light. And she goes, bop, 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 and the dust from the chalk is there. Do you see what I'm saying? And she says,
We'd like to go home now.
yeah, she said, think about it. See what I'm saying? Basic. But it always kind of interests me. I always play with battery fighters. I do. Maybe not you. I love it. I love science.
Well, that's great to hear. We love science too, and I think we're going to have to call it a night. So thanks, everybody. We're going